Okay, assalamualaikum everyone. Today we have to look at the conduction experiments. So you have studied both modes in theory, the linear conduction and the radial conduction. The conduction is the heat transfer from one end of the material to the other end of the material due to the vibrational motion of the atoms and the movement of electrons. Now you see there are basically two modules there. There is the one is the linear module here, and the other one is the radial module here. That one is used basically to study the linear conduction here, and this one is basically used to study the radial conduction here. The equipment we have to use in our lab is basically belongs to Soltec model HE105 heat conduction study bench. You can download the manual online if you need to. Okay, in this experiment what we have to do, the objective of the experiment is to basically determine that we have to calculate the thermal conductivity of a solid material. In the previous experiments we have also found the thermal conductivity of the liquids and the gas, but now we have to look how we can calculate the thermal conductivity of a material, of a solid material or of a metal using the Fourier's law of heat conduction. Okay, so coming to the control panel, okay, you see there are two displays. The one is the heated power display and the other one is temperature selector. Okay, so using this knob I can control the heated power, and using this one I can read the value of the temperature I need to read. Okay, so first of all, before starting the experiment, now you can see this is 32.2. That's the temperature of T2 because I have recently basically turned off the heater. Now keeping from the back of the end, there exists the heater button from where you can turn on the heater. So before starting the experiment you have to check two things. First, this heater must be turned on, and the other one is you have to check the water supply, okay, whether the water is on or off. Okay, so make sure the sufficient amount of water is circulating through the equipment, otherwise this will melt out. Okay, so to avoid the melting of this plastic, so you have to just make sure the proper circulation of the water. Okay, first of all we come to the radial conduction module that have been available here. That's the radial module here. So you see there are 6 temperature sensors: T1, T2, T3, T7, T8 and T9. There are 6 temperature sensors from where I can take the readings of the temperatures. Inside this plastic box there is a brass plate of diameter 110 mm, and the thickness of the plate is 3 mm. On the bottom side you see this one is the water inlet and this one is the water outlet. So the water comes inside, circulating in the outer periphery. The water circulates in the outer periphery and then absorbing the heat, leave the equipment, leave this module, radial module. Okay, so before starting the experiment I'll set the value of the heater power from here. I'm going to set it at 25. So you have 25 watt. The unit is 25 watt. So I'm going to set it 25, 27. Okay, 27 is 28 is fine. So now you can see there is an increase in temperature at T1. That's basically is at the center of the radial module T1, and then you see the T2 from here, T3, and T4 and T5 and T6 we are not using, so they are they have the room temperature. And then we are using the T7, T8 and T9. One thing you should observe, like we see the decrease in temperature as we move from T1 to from the center of the radial module to the T9. Like T1 is the highest temperature, T2 will be the lower one, T3 is the lower temperature, and then we can observe T7, T8 and T9. Okay, coming to the radial module, you see that T1 is basically installed right above the heater. So you have the highest temperature because the heater is installed at the middle of the plate and the heat conduction is in radial direction. Okay, T1 to T9. So that's why you see the highest temperature at the T1 and the lower temperature T2, T3, 3 as you go from the center of the this cylindrical plate from to the outside of the to the outer periphery. You see you observe the decreasing temperature, and on the outside the water absorbs the heat. So we have to find the thermal conductivity of this material using the Fourier's law of heat conduction. From the theory, you see that the Fourier's law of heat conduction from for the experiment. You see, this is a formula for the cylindrical heat conduction. You have studied in your theory that heat conduction Q dot for the steady heat transfer is basically delta T divided by the resistance. And delta T is the temperature difference. Log nature R2 by R1, 2 by L K. So L is the length, K is the thermal conductivity. I need to calculate this K. I need the delta T, I need the R2, R1, and I need the Q dot, and I need the length. So the length is constant, R2, R1 is constant. So I need two parameters. I need the delta T and I need the Q dot. Okay. So for that, to calculate the delta T, you need basically 2 points on this whole on the cylindrical bench. So you can choose any 2 points, R1 and R2, and on these 2 points you need to measure the temperature, the delta T you get from there, and then you can using these values you can basically calculate the value of thermal conductivity. Okay, so coming to the equipment, you see I can now I can measure the Q dot from here. That's 28 watt, and to measure the delta T I need to select two temperatures from out of these 6 temperatures, T1 and T9, from where I can use T2 as a R1 and T8 as a R4 R2. So R1 is basically since the distance between two temperature sensors is 10 mm from this one and to this one, so 10 mm, 20 mm, 30 mm, and the 40 mm. So T8 would be at 40 mm. So I can use the R1 as 10 mm and then R2 as a T8 in 40 mm. And I need to basically these two temperatures are required, T2 and T8, to find the thermal conductivity of this material. Okay, so when this I'll wait until this temperature T2 gets stable. So right now you can see this one is the temperature on the screen on T2 is 41, and I'll wait until it gets stable. It seems quite stable, but I'll still wait a bit so that it gets stable. 41.1. Okay, so you have to wait until this one gets stable approximately. So I can assume this one is stable because 41 this is going to vary between 41.1 and 41.2. So T2 41.1 and I need the T8. I can read from here 34.3, 34.4. So using these two temperatures I'll get the delta T and I know the value of R1 and R2. The length or the thickness of the brass sheet, the brass plate inside this plastic box is 3 mm. So you have to calculate. You have to use the length. The length in this direction is basically 3 mm. So you can use the value of L 3 mm. So using this, you can find the thermal conductivity from for the brass materials. Okay, coming to the linear module, you see there are 9 temperature sensors, and this one is basically in three sections. So this one is heater section. There are three temperatures, T1, T2, and T3, and this one is the cooling water section. So T7, T8, T9, and their middle section T4, T5, and T6. Okay. So similarly, you have to calculate the thermal conductivity using the Fourier's law of heat conduction. You have to, in one dimension, you can calculate the thermal conductivity. You can draw the temperature profiles of this one. Similarly, you have to draw the temperature profile for the cylindrical one as well. So what you can see, you can withdraw the middle section. This one is basically made of brass with diameter 25 mm, and these two are also made up of brass. the heater section and this cooling water section is also made up of brass. So I'm going to install this one again at this place. So make sure, like, after inserting the middle section, make sure that this one should be tightly this inner the middle material should be tight using the L key from this nut. Okay, so there this one is cooling, and you see we can insert the water pipe from here, the cooling end. The water will come inside from this end, and by absorbing the heat at this end, so the water leaves using from this knob. Okay, so similarly we will do the experiment in this one. We'll turn on the heater. The heat will conduct in radial in one dimension. So T1, T2, T3, we will observe the highest temperature T1 and the lowest temperature T9, and what we have to do, we have to measure the thermal conductivity. So we can measure the thermal conductivity brass from either end using this end or this end, the heater section or the cooling section or the middle section, because all three are made up of brass. Okay, to calculate the thermal conductivity, like we know from the theory that the Ford's law of heat conduction for one dimension is basically, you see that Q dot is basically minus Ka del T, the temperature gradient, and releasing that Q dot is Ka delta T by delta X. And you see there is a wall, and on the left side you see the temperature T1, on the right side there is the temperature T2, and the area perpendicular to the heat transfer is A, and K is the thermal conductivity, and delta X is the thickness. Okay, so using all these parameters we can find the thermal conductivity K. Q dot we can get from the heater, and A is the area perpendicular to the heat transfer. We can measure this area heat transfer from the brass section. So that's 25 mm diameter, and delta T and delta X. So I need to basically calculate the delta T. So I can, out of these 9, I can use any 2 temperature sensors so to calculate the thermal conductivity of the brass section. So I'll use this T4 and T6, this middle one, T4 and T6. You can calculate, you can either use T1 and T3, but don't use T3 and T4, because there is a contact between the two surfaces. Since the contacts are not perfectly contact due to air gaps, there exists the thermal contact resistance between these two. So while observing the you must also see that you will observe the certain temperature jump between T3 and T4 and T6 and T7, showing that there is the air gaps. So to avoid that, we must tight it as possible as we can. So using I can use T4 and T6 as the temperature difference, and then delta X will be between them, since these are 2 temperature sensors. So one end to the other end is 10 mm. So using delta X is equal to 20 mm, and the area perpendicular to the heat transfer we can calculate from the diameter, and then Q dot can be calculated from this one. Same procedure, the reading will be given to you in the class material section. Using that values you can basically analyze the data, and you can see how the heat conducts in the linear direction. You can observe the decreasing temperature as you go away from the heater section to the cooling end section, and you can also observe the temperature jump between the temperature sensor T3 and T4 and T6 and T7, and that's basically the outcomes of these experiments. And you can see there are other 2 middle section as well, from where we can perform other experiment as well. So this one is basically also made up of brass. This one is 13 mm diameter. So you can, by installing this one at the middle, you can observe how the area reduction, how the heat transfer decreases or increases. So using this one, so as you know that if the heat transfer, the area perpendicular to the heat transfer is decreased, we observe the change in heat transfer from the heater end to the lower end. So this one is for that, but that's not the experiment of interest for this one. And this one is basically made of stainless steel. This one is again 25 mm, and you can use this one to find the thermal conductivity of stainless steel, but you have to make sure that this one should be tightly held between the heater and the cooling end to measure the approximate thermal conductivity of the steel. Okay, this one is for these two experiments. If you have any question regarding these two experiments, you can ask in discussion section, or you can individually text on Teams. I'll answer your queries. Okay, this one is for this